In the last section, we learned that benzene has some special properties called aromatic. Not only benzene, some other molecules also show aromaticity. The question is, how do we know if a molecule is aromatic? Huckel rule answers this question. Huckel rule, also called 4n+2 rule, it says that a molecule is aromatic only if it's cyclic, just like benzene, it's a ring, and it's planar, it's conjugated. Conjugated means that all carbons are sp2 hybridized. The most common case is when you draw Lewis dot structure is alternate double bond, single bond, and double bond, single bond. Now sometimes a carbon has a p orbital that is empty, that's called a cation, or has 2 electrons on it, and that's an anion. And this is conjugated because the pi electron can go through this p orbital. Now this is not conjugated. You have sp3 hybridized carbon connected to hydrogen. The pi electrons cannot go through this carbon, and so it's non-conjugated system. There is one more requirement, and that is it contains a total of 4n+2 pi electrons. So n is an integer. It can be 0, 1, 2, 3, 4. So when n is 0, you have 2 pi electrons. When n is 1, you have 6 electrons. When n equals 2, you have 10 electrons. So if the system meets all these requirements, it's aromatic. The Huckel rule, also called the 4n+2 rule, says that a molecule is aromatic only if it is cyclic, just like benzene, it's a ring, a planar structure, a conjugated system. Conjugation means all carbons are sp2 hybridized. The most common case is when you draw Lewis dot structure. It is alternate double bond, single bond, double bond, single bond, just like benzene. Now sometimes a carbon may have a p orbital that is empty, and that's a carbocation. Or it has 1 electron, and that's a radical. Or it has 2 electrons with a negative charge, and that's an anion. And this is still conjugated because the pi electrons, they can go through this p orbital, and they are conjugated. Now this is not a conjugated system. When the system contains a carbon with sp3 hybridized carbon, it connects to 2 hydrogens, and there's no way the pi electron can go through this carbon to be conjugated. So this is a non-conjugated system. There's one more requirement, and that is the system contains a total of 4n+2 pi electrons. N can be 0, 1, 2, 3, 4. So when n is 0, it is 2, so 2 pi electrons. When n equals 1, it will be 6 electrons, and that's a benzene. When n equals 2, that will be 10 electrons. If a system meets all these requirements, it is aromatic. If a molecule meets all the requirements mentioned above, that molecule is aromatic. Aromatic system has characteristic properties. It has special chemical stability suggested by heat of hydrogenation. It gives substitution reaction instead of addition reaction, and it shows ring current in NMR. Just like benzene, the range of hydrogen from 6.5 to 8, and in carbon-13 it will be 110 to 140 ppm. If a molecule obeys the 4n+2 rule, then it's aromatic with unusual stability. On the other hand, if the molecule meets all the requirements except the last one, instead of 4n+2, it is 4n electrons, then the molecule becomes very unstable. It's called anti-aromatic. So an aromatic compound is more stable than a non-aromatic compound. But anti-aromatic compound is even less stable than a non-aromatic compound. Now, many compounds may appear to be anti-aromatic, but adopt structure to be non-aromatic. For example, cyclooctyltetraene. Now, this compound has 4 double bonds, and 1, 2, 3, 4. So it has 8 pi electrons, and that's 4n. Now, this is a cyclic molecule, and if it's planar, then it meets the requirement meant to be anti-aromatic, to be very unstable. Instead, the molecule avoids to be unstable, so it adopts the real structure, adopt a non-planar structure. In this way, it's not anti-aromatic, all right? So it's just a non-aromatic. It's a regular molecule with 4 double bonds, and it reacts with bromine, potassium permanganate, hydrogen chloride, as if it were just a molecule with 4 double bonds. Another example is cyclopentadiene. Cyclopentadiene is a cyclic compound planar with 4 electrons. So 4 electron is 4n system, and therefore it's anti-aromatic. Because it's anti-aromatic, it's so unstable in nature, it doesn't exist as a isolated cyclopentadiene. Instead, it always combines 2 together to form a dimer. A dimer is non-aromatic, not anti-aromatic. You may remember this is the molecular orbitals for benzene, a lowest energy molecular orbital that can hold 2 electrons, and then above it a pair of molecular orbitals that can hold 4 electrons. Now, if the molecule is bigger than benzene, then you may have another pair of molecular orbitals, another 4 electrons. So 4n, that's this one, plus 2, that's the lowest energy level, means that a system with all the bonding molecular orbitals are filled with electrons, and that makes molecules very stable. If the molecule has electrons different from 4n plus 2, and that means you may have electron go to this anti-bonding molecular orbital, and that make molecules unstable. Or you may lose electron from the bonding molecular orbital. Again, it makes molecules unstable. So 4n plus 2 is the most stable electronic structure for cyclic conjugated system. Not only neutral molecules can be aromatic, ions can also be aromatic as long as they obey 4n plus 2 rule. For example, in cyclopentadienyl anion, this molecule have 5 carbon with 2 double bonds, and there's a carbon that has 2 electrons. These 2 electrons in a p orbital that is perpendicular to the plane. Now, if you count the electrons, each pi double bond, okay, each carbon has a p orbital that has 1 electron to form a pi bond. So each double bond has 2 electrons, and here 2 electrons. So altogether, 2 plus 2 plus 2 is 6. And therefore, cyclopentadienyl, although has 5 carbon, it has 6 pi electrons. Now let's look at the cycloheptatriene cation. So this molecule has 3 double bonds, but with a carbon has a positive charge. A positive charge means a p orbital that is empty. There's no electron in it. And so double bond, each carbon has 1 electron. So 1, 2, 3, 4, 5, 6. Again, you have 6 pi electrons. All right. So both of these molecules, they are cyclic, conjugated planar structure, and they have 6 electrons. Although one has 5 carbon, one has 7 carbon, both are aromatic. Let's start with the cyclopentadiene molecule. This molecule is a neutral molecule with 2 double bonds and a sp3 hybridized carbon, and the carbon has 2 carbon-hydrogen bonds. And this molecule is not a conjugated system, and therefore it's a regular alkene with 2 double bonds. And for a regular alkene, we call it non-aromatic. Okay, so any alkene is called non-aromatic. Now, if this molecule loses a hydrogen with 2 electrons, then this carbon will become a cation. Okay, the 2 electrons all go to the hydrogen, so it's a cation, and therefore now it's a cyclic system, planar structure with 4 electrons, and the 4 electron 4n, and that's anti-aromatic. Okay, note that we start with a regular alkene or non-aromatic compound. We make an anti-aromatic compound. Anti-aromatic is unstable, extremely unstable. If a molecule is very unstable, it is very high energy. So the reaction go high energy is difficult, and therefore this reaction is very hard to perform. Okay, difficult to form, to go high energy. Now, if you lose a hydrogen with 1 electron, then the carbon will keep 1 electron, and this is a radical. Radical is also unstable, so it still goes to a high energy, and this reaction is difficult to form again. Now, if you lose a proton, and the 2 electrons remains in that carbon, okay, so now you get a cyclopentadienyl anion, and this system has 6 electrons. Okay, so a cyclic planar structure with 6 electrons, and that is an aromatic compound, remarkably stable. And when a compound is very stable, it has low energy, and therefore this reaction will go easily. Okay, so it's performed much easier than the other 2 reactions. When we draw Lewis dot structure of cyclopentadienyl anion, we usually put 2 electrons on 1 carbon. In reality, the system is conjugated. The 2 electrons can move to other carbons. In effect, the molecule is symmetric. All the carbons are the same. All carbon-carbon bonds are the same. In the last slide, we show that cyclopentadienyl anion can be made from cyclopentadiene neutral molecule by losing a proton. If a molecule can lose a proton, that molecule is acidic. For example, hydrogen chloride can lose a proton to form chloride. So hydrogen chloride is an acid. Now, because cyclopentadiene can lose a proton to form a stable aromatic compound, the reaction is relatively easy, and therefore this is an acid. In fact, 1,3-cyclopentadiene is one of the most acidic hydrocarbons known, with pKa 16. Now, usually a double alkene has a pKa around 40, and water is 16. So water is much stronger than alkene. Okay, remember, the smaller the pKa, the stronger the acid. Here, cyclopentadiene has a pKa comparable to water, and this is because it forms a stable aromatic compound when lose the proton. Cycloheptatriene contains 3 double bonds. However, because it has a sp3 hybridized carbon, this molecule is not a conjugated system, and therefore it's non-aromatic. It's just like a regular alkene. When it loses a hydrogen with 2 electrons, it forms a cation. Now the system becomes conjugated with 6 electrons, so it's aromatic. Again, because it's conjugated, the cation can move to any carbon. The molecule is symmetric. So all the carbons are the same, all the bonds are the same, just like benzene. Okay, for this conjugated system, several resonance forms are needed to represent the real structure. Cyclid compounds containing nitrogen, oxygen, sulfur, phosphorus are called heterocyclic compounds. Heterocyclic compounds can also be aromatic. Here shows two examples of heterocyclic aromatic compounds. One is pyridine. The structure is similar to benzene, but the one carbon is replaced by a nitrogen. Nitrogen usually forms 3 bonds with a lone pair electron. For example, ammonia NH3, okay, 3 bonds with a lone pair electron. Okay, in pyridine, nitrogen also have 3 bonds, a double bond and a single bond with a lone pair electron. In the structure, nitrogen uses 1 electron in its p orbital to participate in the aromaticity. Okay, in this way, the total pi electron will be 6 electrons, and the lone pair electron pointing outwards that does not participate in the aromaticity. And because these 2 electrons does not participate in aromaticity, it is available for reactions. For example, ammonia is a base because it can react with a proton. Similarly, pyridine is a base because it has a lone pair electron that is available for reactions. It can react with a proton. The other example is pyrimidine. This molecule is also similar to benzene, but the 2 carbons are replaced by 2 nitrogens. Again, each nitrogen uses 1 electron for aromaticity, so that the system has 6 pi electrons, and both has lone pair electrons pointing outwards that do not participate in the aromaticity, and therefore pyrimidine is also a base. Pyrrole is a 5-membered ring with 2 double bonds and a nitrogen. Each double bond has 2 pi electrons, so 2 double bonds means 4 pi electrons. For the molecule to be aromatic, nitrogen must contribute 2 pi electrons, so that the total pi electron is 6. In this case, the lone pair electron of the nitrogen now is in the p orbital to participate in the aromaticity. Because the lone pair electron participate in the aromaticity is not available for reactions with protons, and therefore Pyrrole is a very weak base, much weaker than pyridine and pyrimidine. Imidazole is also a 5-membered ring, but with 2 nitrogens. For the molecule to have 6 pi electrons to be aromatic, 1 nitrogen must use 1 pi electron, and the other use 2 electrons, or the lone pair electron. The one donate 1 pi electron still have a lone pair electron that pointing outwards, and these 2 electrons is available for reactions, and therefore imidazole is a base. Example: thiophene, a sulfur-containing heterocycle, undergoes typical aromatic substitution reaction rather than addition reaction. Why is it aromatic? The structure contains 2 double bonds. Each double bond is formed by 2 p orbitals. So you have 4 p orbitals on the carbon. So 1, 2, 3, 4. Okay, and the sulfur contains 2 lone pair electrons. One is in the p orbital, one is pointing outwards. So the pi electrons altogether is 4 plus 2, that's 6 electrons. Okay, and therefore this molecule is a planar, cyclic, conjugated molecule with 4n plus 2, that's 6 electrons, and therefore this is aromatic. Here shows some biological molecules that are heterocyclic aromatic compounds. Here shows some polycyclic aromatic compounds with fused rings: naphthalene, anthracene, benzopyrene, coralline. Naphthalene contains 2 benzene rings fused together. it has 10 carbons. It is aromatic because each carbon has 1 electron in its p orbital, and the total pi electrons is 10. Therefore, this molecule is planar, cyclic, conjugate system with 10 electrons, which obeys 4n+2 rule. For this molecule, we need 3 resonance forms to represent the real structure. As an aromatic compound, naphthalene undergoes substitution reaction instead of addition. So when we add bromine to naphthalene, no reaction takes place unless a catalyst ion is added, and the product is a replacement of one of the hydrogen by bromine. Aromatic compound can be analyzed by infrared, UV, and NMR spectroscopy. In proton NMR, the range is from 6.5 to 8 ppm. As we explained before, due to the ring current, an induced magnetic field opposes the applied magnetic field inside the ring, but parallel to the applied field outside the ring. And the consequence is that the hydrogen outside the ring feels de-shielding effect, and the hydrogen inside the ring has a shielding effect. And this is called anisotropic. For example, 18 annulene has 18 carbons and therefore 18 pi electrons. 18 equals 4 times 4 plus 2, and that's 4n+2 rule, and it is a cyclic conjugated planar structure, and therefore this is aromatic compound. Hydrogens around the ring or outside the ring has a chemical shift 9.3, and that's due to the de-shielding effect. And the hydrogens inside the ring has a chemical shift -3, and that is due to the strong shielding effect. Here is another example. P-bromotoluene. The methyl group hydrogen has a chemical shift around 2.3, and the benzene ring has 2 types of hydrogen, A and B, A and B, and both has a chemical shift in the range 6.5 to 8. In carbon-13 NMR, aromatic carbons have chemical shifts ranging from 110 to 140. For example, benzene has 1 absorption, 128.4 ppm. Exercise. The first molecule, called the Cycloheptatriene, and this compound is stable. But the second molecule, Cyclopentadienyl, and this compound is so reactive, it can't be isolated. Explain, taking the polarity of the carbonyl group into account. So let's look at the first molecule. Now, sometimes it's helpful if you draw the resonance structure. And the resonance structure in this molecule, we can push the 2 pi electrons to oxygen. So here is another resonance structure. Okay, because the electrons goes to oxygen, so oxygen now has 8 electrons with a negative charge, but the carbon becomes positive charge because it's loose electron. Okay, so now you can see this ring. Okay, it has 3 double bonds. That's 6 pi electrons, and the carbon is a cation with no electron. So the total pi electron is 6, and this planar conjugated cyclic system with 6 electrons. It's aromatic. Okay, and because it's aromatic, this molecule is stable. Now let's look at the second one. Again, we draw resonance structure. We push the 2 electrons to oxygen. So now here is the resonance form. Again, the 2 electrons go to oxygen. It's negative oxygen, positive on carbon. So here we have a ring with 2 double bonds. That's 4 electrons. All right. The carbon is a cation, so no electron. Total 4 pi electron, and that is 4N is anti-aromatic. Anti-aromatic is very unstable, and so it's so unstable that it cannot be isolated. Homework questions. Problem 15.1 to 15.3. These three questions are about naming. I forgot to put in the last video, and I add here. Please work on these questions. Problems 15.5 to 15.12 are about aromaticity. And if you want to be really good at organic chemistry, you need to do more practice. So work on some additional problems.